All right, good afternoon. My name is Ryan Holger. I'm with Temperature Equipment Corporation. This week's webinar is on CO2-based demand control ventilation systems. If you have any questions as we go, type them down in the question/chat box on the bottom right-hand side of your GoToMeeting tool, and I'll stop periodically and try to answer some of those questions. So we're going to go through numerous topics here today, mainly focusing on the fundamentals of how to control a system with CO2 sensors, but we will also talk about various code requirements and utility incentives that are available in order to help you do this kind of stuff. So how do we control most buildings? Normally we just control buildings based on temperature. Unfortunately, there's many other factors that go into that. Many of you guys are students of ASHRAE Standard 55, and you know radiant temperature, humidity, air velocity, clothing level, and all kinds of things like that come into play. But ventilation is also a component of that. You've often been in buildings and you've heard someone say that it's stuffy or drafty, or you've even said that yourself. So temperature is not the only thing we should be controlling. There's numerous variables, and ventilation is going to be one of those. Unfortunately, the way we provide ventilation in most buildings today is the same way that we've always done it. It's pretty much the same deal. This is a chart of our historical ventilation rates over time. The first, 100 years or whatever are just various municipal codes that may have had a ventilation requirement, although many places did not have a requirement at all. The bulk of our current building stock is built in the 1900s. As you can see there, 10 CFM per person was a pretty common ventilation requirement from pretty much the main building boom age in the 1950s on through the 1970s. Then in the 70s we had the energy crisis, if you will, which caused everyone to freak out and try to save energy in unique ways. And even ASHRAE freaked out a little bit, and we cut the ventilation rates basically in half, down to 5 CFM a person, which was obviously too low. And in the early 80s, we had the sick building syndrome. I'm not blaming that on the ASHRAE ventilation rates, but that certainly magnified the problem that we didn't have as much dilution there. So that was quickly adjusted in 1989 to get us back up to 15 CFM per person. And then for a short time, we had 20 CFM per person. And now it's kind of it's a combined number now between per person and CFM per square foot. And the average office building with an average density is about 17 CFM per person. The way we do it now with ASHRAE standards is we take the CFM per person requirement and the CFM per square foot requirement and add them together. For example, in an office building, it's required that you have 5 CFM per person plus 0.06 CFM per square foot. So then you add those two numbers together, and for a typical density of people, it ends up being 17 CFM per square foot for an office building, or per person for an office building. But what you can see here, though, is that pretty much all the buildings that we've built, with the exception of the few for 5-6 years in the early 2000s, with the exception of those, everything else pretty much had a lower ventilation rate than we have today. So as you're going in and retrofitting buildings, chances are you're going to need to bring in more outside air than you used to bring in, which means your energy consumption for your outside air conditioning for heating and cooling is going to go up. So what we're proposing is that you're using demand control ventilation to try to minimize that additional energy penalty on your retrofits. So this is just a little cheesy example here of a typical space designed to the old standard of 20 CFM per person. If you had a space with 25 people, that would equate to about 500 CFM of outside ventilation air that was required. However, if during a particular time this little bank only had 5 people in it, we would still be bringing 500 CFM total. And if there's only 1 person in there, we would still be bringing in the 500 CFM. Obviously, that's more air than we need, and we'd like to reduce that. Now, we can't reduce it down to just 20 because there's other things that are going to be happening in here, like VOCs and building pressurization, but we certainly don't need the 500. So what we want to do is find ways to reduce this outside air. Zoning systems have a similar scenario. We have a fixed amount of outside air coming in at the outside air handler, and there are 2 problems with this scenario. One is, on many of these systems, we have variable frequency drives on the fan, and as those fans slow down, our fraction of outside air changes significantly, and we are bringing in more or less air than we had originally planned. So they may be set up correctly on a full design day, but then as we ramp the fans down, it's going to increase our percentage of outside air inadvertently, which costs us extra energy. The second problem with this kind of system is that we don't necessarily know where all the air is going. Bringing outside air into the air handler, but then as the individual zone dampers modulate back and forth, some spaces become overventilated and some spaces become underventilated. So as you can see here, red is underventilated, blue is overventilated, And nothing is perfect because we made this graphic to look like nothing's perfect. No, but we'll talk about this more in a little bit here. But there are problems with the zoning systems if we're not tracking where the people are at. So what we're proposing to do on these systems, and what we've been doing for at least I've been doing for 12 years at my office, is put in ventilation sensors. And the way we normally do that is with a CO2 sensor. And in reality, we're not directly measuring ventilation. We're measuring ventilation as a surrogate of how many people are in space. But as you'll see in a little bit with the ASHRAE standards, that is an acceptable and desired way to do it. So instead of having a temperature sensor sitting on the wall, what we'd like to do is put a temperature/CO2 sensor on the wall. And in a perfect world, we'd like to throw a humidity sensor in there as well. But I want to push my luck today. If I can get you to put 2 of the 3 sensors in there, we'll be in good shape. All right, so the goal here is to get the fresh ventilation air to the right place, the right room, at the right time when people are actually there. As people move around the building, I want to make the outside air move to the room that they're in. That's kind of my goal here. So how do we actually do this? All right, the first thing is we're going to look at is some of the standards involved in here. ASHRAE 62.1 is our national ventilation standard, if you will. The International Mechanical Code is our national code, but all the data for that pretty much comes out of ASHRAE 62. It's the backbone of how we ventilate commercial buildings. ASHRAE 62.2 would be how we would do it residentially. Additionally, there are the energy standards and energy codes that come into play. And ASHRAE standard 90.1 is our model energy standard for the entire country. And the International Energy Conservation Code, which most municipalities and states adopt, does follow the same language as the 90.1. So pretty much everything begins with ASHRAE. And as you're going to see here in a little bit, ASHRAE advocates using CO2 sensors to ventilate spaces, and in some cases it's actually required. I want to point out, though, that CO2 sensors are a way to measure how many people are in the space, or more accurately, how many people are breathing in the space, and they are not an indication of direct indoor air quality. Indoor air quality is a function of many factors, and it's not just the people and the outdoor ventilation rate. There are other things that could be going on in the building that are improving or decreasing the indoor air quality. So this is just a way to measure how many people are there and correlate that to how much ventilation the code will make me bring in. Second thing I want to point out is that a CO2 sensor is significantly different than a CO sensor. I know that sounds mundane to most of you. However, every single day I get people calling me asking for CO sensors for their office buildings to modulate their ventilation dampers. So they're not getting it. So I just want to point out CO2 sensors are carbon dioxide. It is not a contaminant. It is not harmful to people unless it's in extremely high quantities that you would not find in nature. It's a colorless, odorless gas. It's all around you. Plants are giving it off, and humans are, people are giving it off, and plants are giving it off. People breathe in oxygen and exhale CO2. Plants, if you will, breathe CO2, if you want to say that, and exhale oxygen. That's probably the cleanest way to say it. People exhale CO2, plants inhale or absorb CO2. But you got to get to pretty high levels, around 30 to 40,000 parts per million for it to be harmful to people. And inside most spaces, when you measure it with a meter, you're going to find most spaces will be between 500 parts per million and, say, 1,500 parts per million. Carbon dioxide, on the other hand, is a product of incomplete combustion, and it is significantly harmful to people. But they sound similar, CO and CO2, two different things we're talking about. So CO2 is exhaled by people at a rate of about 40,000 parts per million directly at your mouth. However, it disperses rapidly throughout the room. It's similar to humidity in that it moves east to west, north to south, up and down. Basically, every CO2 molecule wants to get equally far apart as another CO2 molecule. So it spreads evenly throughout a room. So it doesn't really much matter if you measure CO2 at 4 feet above the floor, or if you measure it at 6 feet above the floor, or 8 feet above the floor. It's basically going to be the same value. If you give it a couple more minutes, it'll even out. CO2, however, is a production of what people are doing. The more activity you're doing, the more you breathe, and the more you breathe, the more CO2 you exhale. So when we look at some of the ASHRAE formulas here in a minute, you'll see that the ventilation rates are directly correlated to what activity people are doing. For example, down in this chart here on the bottom side, we have 0 to 5 metabolic units. Metabolic unit is a measure of activity level. It basically comes down to a watt factor. But if you look at that metabolic rate of 1, that's basically someone sitting there and doing nothing, motionless, if you will. If you're working in an office building, you're at a metabolic rate of about 1.2. which means you have a little bit of activity level. Basically, you're typing on your keyboard and moving your mouse, thinking with your brain a little bit, so it uses a little bit more energy. And when you're sleeping, it's slightly less than 1. However, if you're working, running on a treadmill or playing a basketball game or something like that, you're probably going to have a metabolic rate of 3 or 4. So hence, we need to ventilate those types of spaces with a higher outdoor air concentration. And the main reason we're ventilating spaces with outside air, at least for the people purposes, is to dilute body odors from people. So it actually works out kind of nice that the more you breathe, the more body odor you have, and those kind of things are linked together. So if we track your CO2, we are doing a pretty good indication of tracking the ventilation requirements. I often get the question on how long is it going to take for my CO2 sensor to react. And the way I usually answer that is, well, it depends on how much you're ventilating and how many people are coming and going into the space. But basically, if we assume a bunch of people go into a room and that quantity of people stays the same, so let's say 15 of us walk into a conference room and nobody else is coming or going, we shut the door, the amount of time it takes for that space to register our CO2 levels and to level off to a neutral point is dependent on how much ventilation air I'm bringing in. If I'm only bringing in 5 CFM per person, you can see on the curve here, it's going to take 2 to 2.5 hours to get to a fairly level point. However, if I'm bringing in 10 CFM per person, it'll take about an hour. If I'm bringing in, what did we say before, 17 CFM per person is a common building, it's about a half an hour or so before I get to a reasonably level line here. And then I'll be reacting to that. So it doesn't take very long at all. I know a half an hour sounds like a long time, but in the thermodynamics of an entire building, it's not very much time at all. And most ventilation standards do allow you as much as 2 hours of non-ventilated time if you want, although there's no reason to do that, but you could theoretically do it. So getting there in a half an hour is plenty of time. All right, so this is the magic. This is the formulas that are in the ASHRAE standards that basically allow us to use CO2 sensors to ventilate spaces. Not only does the ASHRAE standard allow us to do it, the ASHRAE standard and its ventilation rates are based on this fact. This is how the numbers in the table were derived. So when someone tells you you need 5 CFM per person or 20 CFM per person or whatever it's going to be for a given space, those numbers came out of this formula originally. That's how at ASHRAE we decided how much outside air to bring into a given space. We took the CO2 levels and the people generation and backed it out. So this formula kind of divests itself down into a simplified version, which I'll show you right here in the interest of time. Basically, the outdoor air rate per person that we need is a function of a constant, 8,400, and that constant's coming out of all this gibberish over here. 8,400 times the metabolic rate. So my little calculator here, if I'm in an office building and I got a MET rate of 1.2, which is a common office building, times 8,400, that gives me 10,000 and change. And then if I want to find the rate per person, I would need to divide that by the difference in CO2 levels. So let's say that it's a 1,100 outside and it's 400 inside. That's a difference of 700. So if I divide that 10,000 by 700, I come up with 14 CFM per person. And I can work this equation multiple ways. If I know the ventilation rate that I want, the R on this equation, and I want to solve for the CO2 in the space I'm targeting to find my set point, so CR on here, I can do that exact same thing. 8,400 times 1.2, so that's 10,000 and change, right? So 8,400 times 1.2 is 10,080. If I divide that by, let's say I want, I don't know, whatever, 17 CFM per person, so divide that, that's 592, and I subtract off my my 400 for my outside air, assuming I have that right now, and it basically, or add 400, excuse me, that tells me I need basically almost a 1,000 part per million set point for the indoor, right, for this particular space. Basically, for office buildings with a typical density, we end up trying to achieve 700 parts per million indoor set point for CO2 above whatever the outdoor is. If the outdoor is 400, I want 1,100 as my set point. If the outdoor is 500, I want 1,200 as my set point. That's usually what it boils down to for an office building. Other spaces like gymnasiums and stuff will work out differently. All right, so let me just look real quick and see if we've generated any questions based on this discussion here. If I can find the little question box. let's see. Bear with me 1 minute. The little questions aren't popping up here. All right, I'll get that fixed in a minute. I'm not sure why the questions aren't populating. All right, I'll work on that as we're talking here. All right, so we go back to our little bank example. 25 people. We design it for 500 CFM of outside air. I still have to size the mechanical heating and cooling systems for 500 CFM. However, if there's less people in the space, say only 5, then I can throttle that CFM back, in this example, down to 100. If there's only 1 person, I can throttle it back even further, in this example, down to 20. Now, in reality, I'm going to have something higher than that just for building pressurization reasons, as well as VOCs of furniture and paint and stuff like that. But in concept, that's what it's going to look like. If I have my zoning system, I'll be able to put a CO2 sensor in each space and modulate his VAV damper according to what his temperature and his CO2 need in that space. And then if one of those guys opens up to a certain point and he still doesn't satisfy his temp or CO2 level in the space, then I can go ahead and tell the main air handler up here to bring in more outside air from the outdoors, not just from the duct system. Some of the components that I'm going to need to do this, I'm going to need a CO2 sensor in the space, obviously. This can be combined with a space temperature sensor or on its own. I'm going to need a VAV box controller that has mathematical algorithms in it that can handle this type of control, or that I can program myself and add those algorithms. And then I'm going to need an air handler controller or rooftop controller that can also handle these sequences. So not only modulate its outside air damper based on CO2 levels, but in our case with a zoning system, go back and look at all of the zones combined to see which one of them is worst off and make sure that he's getting satisfied. I'm going to skip this little video because it's not going to play very cleanly on the webinar, but if anyone wants to see that later, I can show that to you. There are several studies out here that I'll reference. I won't spend a ton of time on them, but there's a few of them here I'll point out. I mean, there's just tons of them that correlate IAQ and CO2 and productivity and things like that. So here's one out of the Department of Energy, Lawrence Berkeley Labs, had a correlation. And by the way, most of these studies now are probably been out there for 10 years at this point, because this is a pretty well-established topic. But a significant correlation was found between decrease in performance and high CO2, or if you want to say it the other way, increased performance with low CO2 levels. Basically, the more ventilation you provide to a space, the more productive people are. However, you don't want to provide more ventilation than you absolutely need. You want to provide enough to make them productive and healthy, but not enough, not so much that you're wasting energy. Here's my favorite study of all time. Air quality and ventilation were ranked number 2 on this tenant satisfaction survey for tenants that were leaving spaces and not renewing their leases. Their number 2 complaint was that it was poor air quality. Usually that was expressed as it's too stuffy or it's too drafty kind of thing. And for you guys that have been to some of my classes before, you already know that number 1 and number 4 are I'm too hot and I'm too cold. And number 3 is some crap about elevators that we don't really care about. But 3 of the top 4 have to do with temperature and ventilation. Another productivity one from the US EPA. Here's a good one because it correlates money. This was a fairly large study with 4,000 employees surveyed in buildings. And basically what the end result of that big long study is that every dollar they spent to fix ventilation and improve that, they saved $2 in sick time. So it's fairly important to make sure we ventilate these spaces correctly, and a CO2 sensor is one way to measure that we're actually doing it. Here's some status on research that was done for schools. Basically 60 million people go to schools every day between the kids and the students. About 14 million of those schools were evaluated as being below standard in terms of their ventilation performance, and 15,000 schools actually were qualified as having unfit air to breathe. So it's pretty serious stuff here. But basically the moral of this here is there's a lot of time that are spent in schools and specifically indoors for that matter. Most people aren't outside like when we were kids. Most kids and adults are indoors most of their day now, and the air quality is not as good because the buildings are tighter and tighter. So I'm not going to bore you with all these studies. They're here if you want to reference them. Like I said, these will be posted online later. If you want to read up on some of these ones in the ASHRAE Journal and stuff, you can do that. So ASHRAE 62.1, as we mentioned, is derived based on CO2 levels to get the ventilation rates, and it also does allow dynamic reset, dynamic changing of the ventilation air to match the CO2 levels that we're trying to achieve. That language from ASHRAE 62.1 feeds into the International Mechanical Code. Pretty much all the language from ASHRAE 62 feeds into the IMC at some point. They do tweak a few things, but it's almost cut and paste. And then in most cases, the local codes adopt the IMC, and they may make some tweaks to that as well. But the ASHRAE standards basically flow into the codes at some point. Since 1999, there's been some implication that we might be able to do something a little different with the ventilation when we added the VRP procedure to that standard to calculate how much outside air we need to bring in. So 1989 is when the standard started referencing CO2 as a design criteria. 1999 is when we correlated this directly to the ventilation rates, but things didn't really start happening until the 2004 version of ASHRAE, specifically Addendum N, and the 2006 version of the International Mechanical Code, which had this specific language here that called out CO2 sensors as a specific means to be able to modulate the ventilation air requirement. So you're allowed to reduce the amount of outside air below the otherwise code prescribed minimum if you're going to measure the CO2 levels in the space and ventilate according to those. So that's really what we're talking about here today. Sometimes there's a misconception that the CO2 sensors are going to make my outside air damper open more when lots of people are there, and hence it's going to cost me more energy to heat and cool. That's not really how it works. It works the opposite of that. I'm going to ventilate your building to the code ventilation requirement, right, whatever it is per person and per square foot, and then when less people show up, I'm going to throttle it back down. So I'm not really going to go above the code air. I'm going to go below the code air. And that's permitted by the International Mechanical Code, ASHRAE 62, as well as most local municipal codes. So here's what it shows you for ASHRAE 62. That's specifically called dynamic reset. And this is basically kind of how it works. This is the same exact language that's in the International Mechanical Code. And this is what's basically allowing me to ventilate based on the CO2 levels. For those of you guys working in the city of Chicago, and I know there's several of you, the city of Chicago also allows CO2 control. It's been in there since the 2003 version of the code. So they were actually ahead of the curve. They were ahead of the national model codes by a little bit. However, it's done a little bit differently there. If you recall, I said with the ASHRAE and IMC, we're basically looking for a difference between inside and outside. For an office building, it's basically 700 parts per million difference between inside and outside. For the city of Chicago, it's a little bit different. They give us a fixed parts per million set point for the indoor occupied space of 1,000 parts per million. So I can't let the indoor space ever go above 1,000 parts per million, whereas if I was following ASHRAE or IMC in the suburban locations or other states, chances are I'd end up with a set point of 1,100 to 1,200 in that range. So the city of Chicago is a little bit more conservative, but nonetheless it does allow us to do it, which is kind of nice because as you guys know from most city of Chicago codes, we're usually behind the national stuff. In this case, the city was progressive and ahead of the national stuff. I get tons and tons of questions about the Wisconsin Ventilation Code, which was most recently updated in 2011. It's very similar to IMC 2009. They do have some amendments to that. But as you read through this stuff, which I'm not going to bore you with by reading it to you right now, it does allow for us to have a varied outdoor air ventilation rate on one of these engineered systems. However, because Wisconsin already has a fairly low ventilation rate of only 7.5 CFM per person, it doesn't afford me a lot of space for modulating it. Because remember, I'm going to have some minimum that's associated with the building itself, VOCs and all that. So I'm going to have a much smaller range to modulate based on the people. So my savings won't be as quick as in other states. However, it is permitted to use this type of technology. All right, let me see if I can get to these question boxes here. I don't know what the deal is with that. Just give me 1 second. There we go. There's the question box. All right, let's see. All right, so we got a question from Robert saying that I assume if you are modulating a VAV box to reduce CO2, there are times you will need box reheat to prevent room overcooling, correct? The answer is yes, that is correct, Robert. However, it should not be any more reheat than you otherwise would have had to use on a non-CO2 job. Because if you remember, I'm not going to modulate any dampers open more than they would have already modulated. I'm going to modulate them down less when less people show up. So I still size the air handler and the reheat coils and everything the same for the exact same capacity. The only difference is if people don't show up, I'm going to modulate the damper down a little bit and provide them less ventilation air, which means I'll use less reheat. But many people do ask that question because they think in their head, oh, I'm going to have all these dampers going further open, which requires more heating and cooling. It's actually the opposite. We're going to modulate it back, modulate it down to provide less when people aren't there. The second question we had come up was from Craig. It says, if it takes 30 minutes or more for the CO2 to equalize, won't you always be ventilating based on the past? A transient room, the ventilation would not match the load. That's true, Craig, to a degree. It takes 30 minutes on, I think it was 10 CFM per person we looked at, to equalize. That's to equalize. It doesn't mean it takes 30 minutes for me to start seeing a difference on the CO2 sensor. I'll start seeing that in a couple minutes. It'll take a while for the space to neutralize, which means that my outside air damper is adjusted to the amount of people that have come in, and I've ventilated for enough minutes to dilute the volume of the air down in the given space. But the sensor will start picking things up right away, and he'll start reacting soon. So he'll say you got 500 CFM per person in there, and you guys that have come to my classroom training have seen this because I put the sensors on the table. But if you got 500 CFM per person in there, and I'm going to have a 50-person class, as people start walking in there, by the time I get to 20, 25 people, I've already seen the CO2 spike up to 700, 800, and then the outside air damper, if I have a CO2 system, would start reacting to that. If I don't have that system, obviously it's not going to react to it, and I'll just get a higher level. So it takes 30 minutes to equalize, not 30 minutes for it to start reacting. Question from Tom is, how do I use a CO2 sensor with a constant volume system? We're going to talk about that in a little bit here, Tom, but it's actually quite easy to do it on a constant volume system because it only requires one sensor, and we'll put that on the wall for a given space. So I'll show you that here in a couple minutes. Javier asks, how effective would a CO2 sensor be if installed in the return air duct instead of the individual zones? The answer to that is it would not be very effective at all. Some codes prohibit the use of return air CO2 sensors. The problem with return air CO2 is I'm getting an average of all the spaces. And if I have an average of all the spaces, I don't know if the ventilation air is going to zone 1, 2, 5, 19. I need to be able to track that air all the way to the given room where the people are at. Otherwise, I'm not going to react to it properly. So, for example, if I have a conference room that's surrounded by 10 private offices, and everybody's sitting in their private offices doing their thing, and I'm ventilating based on the return air, and everybody's happy, if everybody gets up out of their offices and goes into the conference room for a meeting, which is going to happen every day, right? Now there's nobody in the perimeter offices, and everybody's in one single zone. The return air CO2 sensor is going to read the exact same amount because I still got 10 people returning air back to the air handler, but they're all in a different room. So the damper for that zone is not going to be able to bring enough air into that room on its own unless I know that they're all in that room. So I really, on a VAV system or any dampered system, I have to track the CO2 to the zone level. It's the only way to do it. It doesn't necessarily mean I need to have a sensor in every single zone. There are some equations. Equation 6.1 from ASHRAE 62 does allow me to put representative sensors in given spaces and then use that formula to try to track it that way. Only one VAV controls manufacturer that I'm aware of uses that as their standard. Everybody else does it by measuring every single VAV box. All right, let's get back to the presentation here, and then we'll go through some more of the questions here in a couple minutes. If you don't know, you can type your questions in the bottom chat/question box, and we'll take periodic breaks and try to answer them. All right. Just like the mechanical codes feed into the local codes, same thing happens with the energy codes. ASHRAE standard 90.1 is our national model for energy code. That feeds into the International Energy Conservation Codes, which are adopted by most municipalities, either directly or very close versions to that. So in the energy codes, it's often required that I use CO2. So the mechanical codes now allow me to do it, right? Now we're looking at energy codes that are requiring me to do it. And this started with ASHRAE 90.1 2007, and because that language is cut and pasted into IEC 2009, it looks just like this. The 2010 version of ASHRAE looks like this as well, as does the new 2012 version of IECC with a little tweak here I'll mention in a minute. So if you're on the 2009 version of the International Code, which would be the current state of Illinois law and the Wisconsin law, or the 2007 version of ASHRAE, which is the Indiana law, and most states are following one of these guys, right? If you have a space that's of a decent size, in this case 50 square foot or larger, and you have a population density of more than 40 people for every 1,000 square feet, which basically is going to mean training rooms, auditoriums, sporting arenas, places like that, then what I'm going to have to do is put CO2 sensors on there and control to that. If I have an economizer, which the code's going to force me to do anyway, or any one of these other items, but I'm an economizer I'm going to have on every job, so I'm forced to do it. more than 40 people per 1,000 square feet, I have to put a DCV system in by state law, or in some cases municipal law. There's some exceptions to that, like if you have an ERV on there, because the ERV is negating some of the DCV savings because they're both trying to save outside air energy. So you don't really need to have both. You need to have one or the other. Although you certainly could use both and get a little bit more savings if you want. Or if you have systems that are on old pneumatic controls or something like that for zoning systems, then you wouldn't have to do it. If you have single zone constant volume, you have to. Or if you have DDC multiple zone, you have to do it. There's a few exceptions, but you can see here what they are. So mechanical codes often allow it, and energy codes often require it. By the way, when in Illinois as a state, hopefully you guys all know, we're switching to the 2012 IECC on January 1st. The language looks exactly like this, except instead of 40 people, it's 25 people for every 1,000 square feet. So what's that's going to mean, other than conference rooms and training rooms and stuff like that, it's probably going to drive some of your office bullpen areas, your cubicle farms, into having to do the same kind of thing. So just keep that in mind. ASHRAE Standard 189 also has a requirement for CO2 sensors. This is the Green Construction Code. The International Green Construction Code has the same kind of language. LEED recognizes the value of CO2 sensors in this space, and you can earn one of your LEED points by having CO2 sensors, depending on the type of space. If it's a densely occupied space, you use CO2. If it's a sparsely occupied space, you would use outside airflow monitoring stations. All right, so some of the ways to kind of push this along, as if the code wasn't enough to shove it down people's throats. And if I sound cynical, it's because I've been doing CO2 sensors since the year 2000. I've only been in the industry for 15 years, and 12 of them I've been doing CO2 sensors, and it's been kind of a push here. Hang on here, what happened there? The box kind of messed up. So here are the rebates that are available in this area of the country. If you are in Illinois and you have ComEd Electric, there is a rebate for demand control ventilation systems for office buildings and such for CO2 sensors of $30 for every 1,000 square feet, or you can look at it as 3 cents per square foot. That's a prescriptive rebate. You put the sensors in, fill out the form, get your rebate. The Nicor gas, which is in northern Illinois, or NIPSCO, which is northern Indiana, do not have CO2 rebates on their regular program, but you are allowed to do it on the custom program. So Nicor will pay you $1 for every therm you save during the first year. So if you're a ComEd Nicor customer, you can do the first two. You can do the ComEd rebate, get your 3 cents per square foot, then do the Nicor custom application and get $1 for each therm you save over the year. You can combine those two. If you're in Indiana and you're a NIPSCO customer, it's custom also, but you can do the electric and the gas savings on the same program there. People's in North Shore Gas, which is Chicago and just north of Chicago, that is a custom program as well, $1 per annual therm saved. Plus, last month and this month, there's a bonus of 50% more for DCV specifically. So not all custom projects, just custom projects that use CO2 sensors, you get $1.50 per annual therm save instead of $1. And then if you're up in Wisconsin, there's two different ways to capitalize on this. You can use the rooftop optimization program, which is for small tonnage rooftops, and get a rebate of $350 on single zone constant volume systems. Or if you have a larger system or an air handler or a VAV system or something like that, you can choose to use the regular program instead of the rooftop program and get 5 cents for each CFM of outdoor air if you put CO2 sensors in. There's a couple different ways to do that here. All right, let's look real quick and see if any other questions pop up. Nathan says, it has been our experience that CO2 sensors have difficulty with accuracy, calibration, and maintenance. Because of this, sensors are often disabled by building engineers. Have you had similar experience? It seems there must be better options for DCV. All right, a couple different things there. CO2 sensors have had an accuracy issue over the years. I'm going to talk to you about some sensors that came out 6 or 7 years ago that have avoided that accuracy issue. Accuracy on some of those is a calibration guarantee. I'll show you that specifically, but having plus or minus 50 parts per million is pretty much the norm for a decent CO2 sensor. But when you're talking about 1,200 parts per million or something, that's not horrible. The other thing is we're tracking the difference between inside and outside, so we're really more concerned with the difference and less concerned with the actual level. It says there must be better options for DCV. There's probably not. I'll talk about a couple other options in a little bit, but this is probably the best way to do it, and I'll explain why. Jim points out to me that the $1.50 for Peoples in North Shore is actually committed through December 30th, not November 30th, like the other bonus incentives. So thank you for that, Jim. And Matthew points out that in Wisconsin, there's actually a bonus to the end of the year. If you do the rooftop for $350, you can actually get a $15 per ton DCV bonus on top of that. So there's quite a few things here. All right, so let's get off the rebate topic and keep moving here. All right, so our goal is to provide the amount of ventilation for the actual people that are there instead of the assumed people that will be there when we design the building. So that eliminates the overventilation, which eliminates extra heating and cooling energy of that outside air. And we want to do this all with a very good return on investment, which we're going to talk about. So here's your typical building. This is actually a building in Florida from a real building, probably about 10 years ago now. And on the bottom of the scale, you see from 1 to 24, that's the hours of the day. And up the left is from 0 to 100% of the design ventilation rate. This is not 0 to 100% of the damper opening and closing. This is 0 to 100% of the design outdoor air CFM. So in a normal building, we would ventilate to the 100% of the design. So we're moving along, 7 a.m. comes, boom, we turn on the ventilation system. I go to 100%, that's where I sit all day long. Then 5, 6 p.m. comes, I shut it off, boom. So that green area is basically my normal ventilation that I'm doing. In a CO2 system, when we're tracking the actual people that show up, we often find, surprise, surprise, that everybody doesn't show up to work every day. I know it's hard to believe. So we get this purple type profile. We call this a 2-hump profile because it's an office building. So people mostly come in on time, but a lot of them trickle in an hour or so late, or maybe they have different starting times, or maybe they had to go to a meeting beforehand, or who knows what. But everybody doesn't make it to work. Some of them have meetings off-site or whatever it's going to be. Then they leave for lunch, so you get the dip in the middle, and most of them make it back from lunch. And then, like 3 or 4 o'clock, people start cutting out early because they can, or because they have a dentist appointment, or who knows what it is. Almost every building we look at has some kind of 2-hump profile like this if it's an office-type building. It's extremely common. And it's not just from this Florida building, but there's also federal studies that show the same kind of 2-hump profile, where people leave for lunch, people come in late, people leave early kind of thing. Other types of spaces have their own profiles, which are also fairly predictable. Restaurants typically have a 3-hump profile, breakfast, lunch, and dinner. And in fact, they also have these little mini humps for that second wave crowd of people that come in a little bit late. It's just pretty typical thing you'd expect to happen. In some of these given spaces, there's also often a pretty large savings that can be associated with that. For example, in office buildings, you can see here, I'm seeing a 25 to 30% reduction on average, and this was based. These 4 charts are based on average data. I want to say from like year 2000 to 2004 or something like that. But it's similar profiles that you would have now. So instead of ventilating to 100% occupancy, I'm able to ventilate at 70-something in the office building for a couple different reasons. One, everybody doesn't show up all the time, right, which I think you would believe is accurate. And 2, certain spaces aren't always occupied, like the training room or things like that. Retail is a huge savings potential. You can see here, it's basically like a 90% savings potential, meaning I can cut the energy back down to only 10% of what it is on average. And that's because a lot of retail spaces are designed for specific times of year, like Black Friday, which is coming up, or some of those kind of things. So they design for all these people, but on a Tuesday morning at 9:30 in the morning, probably not a lot of people in that space, depending on what kind of store it is. So there's lots of variance available there. Restaurants, similar story. They're designed for whatever the Saturday evening crowd or whatever their peak time is. So there's lots of ability to ramp that ventilation down. This is showing you basically an 85% reduction. However, I will caution you with restaurants. Unfortunately, most restaurants in the dining room area, they've used the ventilation system for the dining room to be the makeup air system for the kitchen exhaust hoods. Obviously, a good design, I'd have makeup air in the kitchen at the hood, but sometimes they don't do that, and they provide the ventilation air through the rooftops in the dining area of the restaurant and suck it through the doors into the kitchen. So if they're doing one of those kind of deals, I can't really cut back the outside air. Otherwise, I'm going to starve off the exhaust hood. If the dining room and kitchen are on their own independent pressure zones, then I can do this kind of thing. And then in schools here, you see it's a big, huge 70% reduction in outside air, which seems kind of unbelievable because hopefully your kids aren't missing 70% of the days of school. There's several things that contribute to that. One is the classroom is designed for 35 or 40 kids, but you only got, 27 or 30 of them in there this year. So there's less kids than you might have anticipated when you design the space. But more importantly is that the kids are not always in the classroom. As most of you know that have kids, They're in the classroom for an hour, then they go to gym, then they go to art, then back to the classroom, then they go to recess, then they go to the library, then they go to lunch. They're bouncing all over different rooms. When I design a normal school, I got to design every room for the maximum number of kids and provide that ventilation air there. But if I track with the CO2 levels what rooms they're actually in, I can throttle many of those rooms back when they're not being used. When there's no kids in the gym, I can throttle it back to some ultimate minimum level that's below the code minimum. Same kind of thing with the classroom or the library or whatever. So it's really more to do with the kids moving around the building than it is that they're not actually showing up for school, although that does happen too. Here's some typical return on investments around the country. It's very common to have these things pay for themselves in under 2 years. On constant volume systems, it's typically faster, sometimes under a year. VAV systems take a little bit longer to pay themselves back because we have less CFM per CO2 sensor. There's studies out there. Here's one of them. The study basically in the first 6 months saved $130,000. Basically a little more than $3,000 per floor of this particular building was saved, 22 cents a square foot. And this study is a 10-year-old study at this point, 12-year-old study at this point. There's a few other ones like it. I usually use this one because it's a federal one, so it's a little more neutral, although it is the federal government, so, you know. But there's plenty of facilities that have been using these things for more than 10 years. Here's an example of some of those facilities that have had 10 plus years. There's some of them that are even more local here in the Midwest, some that should be names you recognize. I'm not going to bore you with that. These will be in here if you guys want to look at these later. But basically, most of them are motivated by having good occupant productivity while saving energy at the same time. That's usually kind of the driver here, and having a reasonable payback period. Hopefully you guys all know Harley-Davidson. There's a bunch of them in Wisconsin that are like that. All right, so the first thing we got to do when we're designing one of these systems is determine if CO2 control is appropriate. I will show you a cheat sheet chart that we often use as a starting point. But things to think about are building pressurization. I don't want to cut back outside air and then have the exhaust system continue running at its normal pace. I got to have those two things linked up in some fashion. So I can cut the ventilation air down, but I don't want to cut it down to be less than whatever the exhaust system is. And the exhaust system for many facilities is just a function of adding up all the total exhaust bathroom fans. If they add up to be 1,000 CFM, I don't want to cut my ventilation air from 3,000 down to 0. I want to make sure it stays above 1,000 to make up the bathroom exhaust. I got to think about any ventilation needs that are being driven by non-people sources, right? So if I got any chemicals or weird things going on in the building, like a laboratory, this is not going to be a good idea to use CO2 sensors. CO2 sensors are for ventilation needs that are driven by the amount of people that are there, not for special processes. This is a chart that we often use to kind of identify quickly if spaces are good or not. Once again, this is like a 10-year-old chart, but it's still pretty applicable today. The way this chart basically works, and I can send it to anyone who wants it, is that if it's an A, it's probably a good idea for CO2 control. If it's a C, it's probably a bad idea. If it's a B, we got to talk about it. So some good candidate examples here, right? In the education environment, classrooms, music rooms, auditoriums, libraries, cafeterias, things like that. Office buildings, any kind of sporting venue is typically a fantastic way to do it. I mean, you got 15,000 people, then 10 people, right? So that's a pretty large variance in amount of people, hence a great idea for CO2. Office buildings, retail establishments. Medical is one we typically stay away from, but there are some spaces we can target, specifically lobby areas, private offices, not the offices where you do the examinations necessarily, but offices where people are, doing paperwork and things like that. Hotels have lots of opportunity. There's tons of conference rooms and meeting spaces that are sporadically used, but when they are used, it's a lot of people. So kind of the theme is, if you got a lot of people and you got a large variance in people, that's when it's going to be good candidates. So we spent sporting arenas, ice arenas are a good one, gymnasiums. You can tell it's a little bit of an old chart because it mentions ballrooms and discos. So if you hang out at the disco, it's probably a good place to do it. Waiting areas. So ones that are bad, the C's, are places that either don't have a variance in people or they have some kind of chemical process. So at a prison, a guard station is a bad case because hopefully the guard station is always fully manned, not half manned. So there's no reason to reduce the outside air because everybody should show up for work. If you got dry cleaners, it's a bad idea because the ventilation is being dictated by the chemicals, not by the 3 guys that work there. Locker rooms are always a bad idea to cut back the ventilation air because in that case, it's really the stinky hockey gear jammed in the locker for 2 months that's generating the smell and the need for ventilation, not so much whether somebody's coming in and out of the locker room. Kitchens are a hard one because your main exhaust is through the kitchen cooking hood, which has grease, so that cannot be run less than it needs to be. So that there's not really a lot of opportunity to modulate anything there. Anything to do with vehicles, like parking garages or car dealerships, can't be done with CO2 sensors. However, we do use CO sensors, carbon monoxide, to monitor those spaces and control the ventilation air. Pet shops are a bad idea because animals smell no matter what, so you want to cut back the ventilation air on those spaces. Depending on what you're doing in a manufacturing facility, it might be a usable idea, it might not. Warehouses are a bad idea because you don't have a lot of people working in a given volume of air. Most medical spaces we stay away from, leave the operating rooms and stuff like that alone. Swimming pools we leave alone because of the chlorine, right? And then all the B's are ones that are maybes, depending on what you're doing in there, right? Like I said, a dining room might be a good example, depending on what you're doing with the kitchen for its makeup air, right? Same with the cafeteria. Or a casino might be a good example if it's a non-smoking casino. But if you're allowed to smoke there, probably not a good idea. So there's some of those kind of factors that get involved here. So like I said, we still design all the HVAC equipment for the full design, which is this top 100% here, for whatever outside air I needed to bring in. Let's say in our example, it's going to be 10,000 CFM, right? And then what I'm going to do is I'm going to modulate that based on how many people actually show up, modulate it below that. However, I'm still going to have some bare minimum of approximately 20 to 30% that I'm going to need to maintain to handle VOCs and things like that in space. I say approximately because it's really a function of the ASHRAE standard and the IMC. Like you heard me say before, we need 5 CFM per person and 0.06 CFM per square foot for an office building. The 0.06 CFM per square foot is to take care of the space VOCs, so off-gassing of furniture, carpeting, etc. The 5 CFM per person one is the one I'm allowed to modulate. When we switched the ASHRAE standards in 2004 and the mechanical code in 2006 to be a per person and per square foot idea, it was specifically with this concept in mind to be able to modulate these two things separately from each other. That is the main reason why we divided the two numbers out. Instead of giving you one lump number, we give you a per person number and a square foot number, and you add them together. That way I can modulate the per person and leave the square foot alone. So in the interest of time, we're going to jump to a couple more detailed things here. So this chart here on the right gives you an idea of what some normal CO2 levels might be and what ventilation rates they correlate to. If you remember that ASHRAE formula I showed you, these two are directly linked. The whole reason we came up with the 10, 15, 20 CFM per person numbers was based on backing the CO2 levels out of that formula. So generally speaking, we're trying to target, primarily something between 800 and 1200 CFM is the pretty normal target. For an office building, like I said, for typical density, it comes out to about 700 parts per million above the outdoor air level. In this part of the country, the outdoor air level is typically 450, which means I often have an office building set point of 1150, which correlates to approximately 15 CFM per person or so here, right? So you can see if my CO2 level is higher, like 2,000, it's only 6 CFM per person, right? If it's low, like 700, it's 30 CFM per person. It's overventilated. If you get a handheld CO2 meter and you walk into any of your customer spaces, chances are fairly good that you'll be able to see one story or the other. Either you're overventilating this thing, which means you're down here at the bottom of the chart and you're wasting energy when people aren't here, right? You're ventilating it for design occupancy, which is not happening at the moment. Or you're underventilating your space, which means you're probably going to have IAQ problems and you need to fix something there to make sure you get enough outside air. So if you're on the sales side of the world, carrying a handheld CO2 sensor is a pretty good way to tell one story or the other. You're going to find very few spaces that are in the sweet spot. They're around 1,000 parts per million. All right, the different ways we can control these sequences. The most simple way is what we used to do 10, 12, 15 years ago, which was just a set point control, which means that I have my ventilation rate coming in, which is the top bar going across here at the 100% line. And then if my CO2 level drops below my set point, say it drops from 1,000 parts per million down to 800, I would say, okay, you know what, I'm overventilating. Let's go ahead and put the damper at its lower position that just takes care of VOCs and not the people. Boom, drop it down here, right? And then a few minutes later, I would see that my CO2 level started increasing again. So I'd open the damper, and I would close it, open it, close it, open it, close it, which is basically ping pong between the design ventilation that the code required and the minimum base ventilation that the square footage portion of the code requires. it would ping pong between those two numbers. It's a pretty crappy way to do it, but a lot of the old Economizer controls could handle it, so that's the way we were doing it. A better way to do it would be to do it proportionally. That's what this chart is showing. Similar kind of thing. The top line here is my regular code design outside air rate, as if everybody was there. This bottom line on the bottom here, this base ventilation, that's the amount of outside air I decided I need to bring in to take care of the VOCs in the space, or building pressurization, or whatever that minimum, absolute minimum driving factor was. And I'll do is modulate between those two. Instead of ping-ponging open, close, up, and closed, I will actually modulate it. So you can see here, I'm looking at the difference between inside and outside. I might start my sequence when there's a 500 CFM difference and end it when there's 1100 CFM difference, with my main goal of being around 700 difference in the middle. All right, and I can put these numbers wherever I want, but if it happens to be 700 between inside and outside, then I would be at the full design ventilation rate. If it's whatever, I don't know, 400, I'd be at half my design ventilation rate, and so on down the line. So no matter what the difference between inside and outside CO2 is, I can correlate that to the damper position I want. And as more people breathe or come in the room or leave the room, then it'll keep tweaking itself open and closed. So this is a much better way to do it than just jamming the damper open, jamming it to a minimum, jamming it open, jamming it to a minimum. I'm going to modulate it much more smoothly. And if I want to take it one step further, I can use a PID loop, proportional integral derivative loop, or in this example, just a PI loop, because derivative is too fast of a calculation for HVAC equipment. So instead of having this red straight line like I had here before, this linear proportional line, I will have various curves depending on what's happening at the moment. Basically, a PID loop just predicts how fast or how slow I'm getting towards my set point, and adjust that accordingly. So this whatever this is, bronze colored thing over here would show me on-off control, boom, 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 boom. The red would be my proportional control, and then my proportional integral derivative PID loop control would be one of these blue lines, which is a much smoother way of getting to where I'm trying to go in a much cleaner fashion. The set point control is pretty much old school. The proportional or PID loop is the more common way you'll see rooftop manufacturers doing it. I just want to remind you guys, if you have questions, type them in the bottom right hand of the screen. Probably got about 10 more minutes of slides here, and then I'll answer any more questions that pop up. CO2 locations, like I hinted to earlier, return mounting should be avoided. The only place that a return air sensor for CO2 would make sense is if the air handler is serving one giant single open space. So if you have one rooftop unit serving a school gymnasium by itself, that might be a good idea. If you have it serving one rooftop unit or one air handler serving a single movie theater, one theater, right, theater number 3, for example, that might be a good idea. I can keep those sensors out of the way and have them correlate directly to their space. However, if I decide I was going to put 2 movie theaters on one air handler, then it's not going to be a good application anymore, because now I'm going to get the average of the 2 theaters. And if one has nobody in it, the other one has 300 people in it, I'm going to think there's 150, and I'm going to ventilate for that. And half the air is going to go to the room I didn't want. So for single zone systems, the only time you put it in the return duct is if it's one giant room with no dividing walls or anything like that. So if you've got a conference space at a hotel and has those 3 dividing walls, don't put one in the return duct. So just only if it's one big space. Other ways you would do it would be to put one in each unique space. So for a zoning system like a VAV system, that typically means one CO2 sensor for each VAV box. So if you got one big open floor plan area and then you got 5 perimeter offices, and each perimeter office has a VAV box, each one of them gets its own CO2 sensor and its own temperature sensor. Then in the big bullpen area where all the cubicle farms are, maybe you got 3 or 4 boxes serving that area. If they're all serving the same area, I can combine them onto a single CO2 sensor, as long as I stay under about 5,000 square feet of coverage. And that's with the CO2 sensor mounted near the center of the 5,000 square foot box. So the sensor itself can handle 5,000 square feet as long as there's no partition walls blocking him. Right, so the best location is wall mounted, 4 to 6 feet off the ground, one sensor for each 5,000 square feet, or if there's partition walls, one sensor for each space. These are just some little cheat sheet charts to kind of help you with that idea. Okay, as far as how we use these, most economizer controls nowadays can accept a CO2 sensor input. So if you got our packaged rooftop unit, if it's a modern one like you're putting in today, it's going to take a CO2 sensor, no problem. If it's an older one, you're going to have to look at the control to see if it has the ability to do it. Most of them do, but it may be that set point on-off type control, but many of them have modulation control. So first you got to make sure you have an outside air damper with an actuator on it, and then make sure it's being controlled by something that can modulate. If it's a DDC control system, you can definitely do it. It's just a function of having one more sensor input to be wired into that controller for the CO2 reading, and then doing the algorithm math to control it. If it's a rooftop, it's going to wire directly to the economizer. These are the typical economizer controls you're going to find in packaged rooftops from all manufacturers. It seems that 95% of the manufacturers use a Honeywell controller, so that's why I threw this chart up here. But you can see here where it has the this indoor sensor input, ISI over here, that's the CO2 sensor on this particular chart. So these three in blue do not have the ability to directly read a CO2 sensor. However, the ones in the green at the bottom all can do it. So each one of these guys can do it. And this W7220, also known as the Jade controller, that as of January 1st, I believe will be the only Honeywell controller available. All the rest of them are being eliminated, and this is going to be the single replacement module. That'll be able to handle that. So you will be able to do CO2 control based on that. All right, we'll skip through this a little bit quickly here, but this is not a new concept. 1916 is the first time we started seeing CO2 measurements show up in the design literature, specifying that you should have, depending on the document, 8 or 10,000 parts for every 10,000, which corresponds to 800 parts per million or 1,000 parts per million, which are very close to the numbers that we use today. And there's been a kind of a history of that a long time. 1929, CO2 levels were noted at 1 part per 1,000, which is 1,000 parts per million in the New York Building Code. Significantly, ASHRAE in 1989 started basing the ventilation rates on CO2 levels. And then in the mid-90s is when we started getting, or late 90s, we started getting this actually written CO2 can be used to actively control it. And 2004 is when everything kind of solidified, and the 62 had all the correct language. 2006 had the mechanical code language. So for the past 6-7 years, it's been pretty well cut and defined on how you can use this stuff. Why it's becoming more popular now, like I said, the mechanical codes allow it. The energy codes are requiring it in many cases. And then the reliability of the sensors is improved, and the cost has gone down. So you can see the cost kind of over time dropping. And just for the record, this is contractor costs. So if you're an end user, don't assume this is the price point, because you still have to pay someone to install this thing, for their markup and profit and all that. But the cost has been driven down significantly. If it's a retrofit, it might cost a little bit more. But as more and more people buy these sensors, the price continues to drop. Most of the CO2 sensors on the market now are designed for a 15-year lifespan, and there are two manufacturers which comprise probably more than half of the CO2 sensors in the market that have calibration guarantees for 10 years, which means you don't calibrate them because they do not drift as much as they used to. And when they do drift, they actually reset themselves. So one manufacturer calls it automatic baseline calibration, ABC logic. The other manufacturer has their own name for it, but it works kind of the same way. Basically, as long as you have, I think it's about 4 hours of unoccupied time a week when there's no people in the space breathing, these sensors basically can recalibrate themselves to match the outdoor air concentration. 4 hours is typically enough time for the CO2 to migrate its way out of the building and neutralize with the outdoor air levels, and then it can calibrate itself back to the baseline. That's what this is kind of showing you here with that little, whatever that is, bronze-colored bar drifting over the days, and then it has to get reset back up to the black bar. This is 3 sensors sitting side by side on a wall with a fairly decent amount of drift between them, as much as 80 parts per million, and over the course of 5 days, they basically calibrate themselves to match each other. Same 3 sensors over 2 weeks, had a little bit of drift between them, and over the course of time, they basically calibrate themselves to match. And the same 3 sensors over whatever that is, 3-year time span, basically calibrating themselves to a neutral level. Like I said, some of these manufacturers have a 10-year calibration guarantee on it. That means if the sensor drifts out of calibration, you get a new sensor for free. In the past 6-7 years since this has been available, I've only had to do that on 2 sensors, and I've used thousands of them. So it is pretty reliable. The accuracy for most of these guys is either 25 plus or minus 25 parts per million or plus or minus 50 parts per million, depending on the sensor, which for something that we're measuring at 1,000 or 1,200, that's a sufficient accuracy level. All right, so kind of the moral of the story is we want to ventilate for the actual people that are there, not the ones that we designed the space for. We want to target spaces that have a fairly decent amount of people in a fairly small space, so a pretty tight population density, and especially if the people are coming and going. So churches, training rooms, movie theaters, offices, classrooms, people coming and going, and quite a decent amount of people, that's where it's going to come into play here. It's allowed by the mechanical codes, required by the energy codes. Paybacks are pretty good. Someone did ask earlier about some other things we can do in lieu of CO2 sensors to activate the ventilation system. One way they can do that is with motion detectors. This basically is not going to allow you to modulate the damper. It's going to allow you to either open the ventilation damper or close the ventilation damper. So in the classroom example, when I said, hey, the kids are going to leave for an hour, leave the classroom, they're going to go to the library, okay, great. When they leave that room, this sensor basically sees there's no one moving in there, and 2 minutes later, it shuts off the lights. Maybe it relaxes the HVAC set points a couple degrees, and it shuts off the ventilation air. Then later on, when the kids walk back in there, see the movement, we turn it all back on. So that's good if you got spaces where it's go or no go. People are there or people are not there, like a classroom, for example. CO2 sensor is going to give you a better controllability when the amount of people is not going to be known. So it could be like a conference room. I could have 0, I could have 3 people in there, I can have 15 people in there, I can have 8 people in there. I don't know what it's going to be, so a CO2 sensor would do a better job in a space like that. A motion sensor would do a decent job in a space where it's going to be occupied or not occupied. Some thermostats have that kind of stuff built in. You guys already know that in some of the residential type environments or hotel type things, they do the key guard slot, cut off your ventilation when you're not there. We can interlock things to security systems on larger DDC systems. So if I have the big DDC system where everybody has the key fob, as you swipe out of the building, I know you're not there anymore. I can go ahead and turn off the ventilation in your private office. Now, that's not going to work for people that are in the cubicle farm, but if you got a private office, you can use this kind of concept. And also set back their HVAC set points and make sure they turn off the lights. So there's different ones we can do to do that kind of thing. There's another case study. I'll let you read that on your own time. Some of these things. There's a couple different tools that we like to use to calculate this. I'm going to show you 2 different ones here real quick just to give you an idea. I won't open up the tool and go through it in the interest of time. But if you want a cheat sheet on how to use it and how to download it for free, I'll send it to you. This is a Honeywell thing. Like I said, I'm not a Honeywell guy, but they have free tools. So basically, you put in some information on the building, name, location, weather data, based on the geography, what town you pick. You pick an occupancy profile pattern. So there's some default ones, office, classroom, etc. Or you can put in your own occupancy profile, your temperature, heating, and cooling set points, and your part per million CO2 set point. You can optionally put your costs in if you know what they're going to be. And then when you hit calculate, it gives you a savings tab like this. I like to use this one because it shows me not just the CO2 savings, but also does economizer and programmable stat. So in this case, I think this was a 5,000 or 6,000 square foot building I plugged in. But having no setback stat cost them $2,400 in gas, $4,400 in electric. At the time I did this, it was $1 a therm, 10 cents a kW on this chart for Chicago weather data. If I add a setback stat, boom, 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 I'm going to save 14%, $940. The next 3 of these were different kinds of economizers with the setback stat. So I go from $940 up to maybe $1,400 in savings. If I add the DCV sensor on there, that would have been $2,000 instead of the $950. If I added the DCV and the full economizer and the setback stat, it was $2,400. Right? So you can kind of get an idea of what these things would save. The DCV by itself is basically 15-20% on this particular building based on the occupancy profile I had picked. So it's just a kind of quick, easy, dirty way to see if a building might make sense. If I plug my costs in, they would have listed here, and then I would have calculated the simple paybacks, which are going to be pretty wide range for CO2 systems depending on what you're putting it on. If you're just going to slap it on a rooftop that already has an economizer, it's going to cost maybe, I don't know, $1,000 to buy the sensor and pay someone to wire it in. So $1,000 when you're looking at something that's going to be, well, got to back the stat out of here, so that's $900. Basically saving $1,000, that's basically a 1-year payback in this example, which is pretty decent. The only thing this doesn't do very well is zoning systems. So when we have a zoning system, we use a different tool occasionally, which is a tool developed by General Electric, by Telair, which in this particular case is branded as Carrier Tool. But you can do single zone or multiple zone systems with this. It's a little bit more of a complex analysis, but it's still fairly easy to use. All right, let me see what other questions we have that have come up. All right, so a question from Robert is, this looks like a nice killer application for VAV systems that use individual room dedicated outdoor air systems We have 2 under construction. Yes, you could definitely do that, Robert. So as long as your air handler has a VFD on it, and you have the ability to modulate the outdoor air damper, and you have the ability to modulate the zone dampers, as people walk into a given space, if they're not in there breathing, you can start throttling back that damper to some predefined minimum, which will also cause your VFD to back down, which will cause your outside air damper to adjust. The only thing I would caution you with on that is some dedicated outside air systems are combined with sensible only cooling systems, such as chill beams or radiant cooling. And in those cases, your dedicated outside air system is also your latent cooling system, because the space cooling systems cannot do it. So you may not be able to throttle back quite as much as you might like, because you might need it for the latent control in the space. Doesn't mean you can't do it. It just means that the rules change a little bit. It's very common for us to do that on dedicated outside air systems, especially in the high occupancy areas like conference rooms and things like that. All right, let's see if there's any other questions. I think we got them all. All right. Well, if anybody has any other questions, you see my email on the bottom of the screen there. Just go ahead and send me an email, ryan.hoger@tecmungo.com, or give me a call, and I'll do my best to answer those questions for you. All right. Thank you very much for your time.